Hi, welcome everyone. I am Sagni Kacharia. I am acting as a TA for the course Machine Learning provided by IT Madras, and this is the fifth interactive session. So I'll be discussing week six content this time, a part of week six content. So the topics that we'll be discussing today are perceptrons and neurons, backpropagation, and we'll also consider some doubt clearing. So before we get into some of the problems, so I'll be solving a couple of problems which you might encounter. Before solving them, I just want to refresh a little bit of the theory. So the weight update rule that we use while using gradient descent is during gradient descent, the weight update rule is, so if I have a weight W, that gets updated as W minus alpha times del J by del W. So here J refers to the cost function. So this is the cost function. And this cost function can change from problem to problem. So now the cost function which we usually use is given below. I'll come to that later. But let us consider a simple perceptron. So here I have my perceptron over here. So it has some inputs, right? It has some inputs x1, x2, x3 with some weights w1, w2, w3, and inside the perceptron, it gets calculated as. So I'll show the z is equal to w1 x1 plus w2 x2 plus w3 x3, and then y is calculated as f of z, where f is the activation function. So f is the activation function, and we get our output y from this perceptron. So now the cost function j will be some function of the target and the and this value y. So the cost function that we usually use, let's say we take a form for that, half of t minus y the whole square. We'll come to deciding this. We will come to differentiating this later on. So we have a cost function j, and the this derivative del j by del w. So del j by del w, I can break it down into. So I can see that j is a function of y, right? So I can get this derivative directly. Now y is a function of z. I can see, right? Y is equal to f of z. So I can do this del y by del z. I can get this derivative pretty easily. And z again is a function of w, right? So z is given by w1 x1 plus w2 x2 plus w3 x3. So based on if w is equal to w1, w2, or w3, we'll get the corresponding derivative. So now let us try to calculate this derivative del j by del w for our cost function, for this cost function over here. So in this case we have del j. So first we'll calculate del j by del y, right? So I'll use some different colors for this. So let's do del j by del y in red. So del j by del y is given by so j is given by half of t minus y the whole square. So del j by del y will be given by minus of t minus y, right? So the 2 comes down, the 2 comes down, it cancels with the half, and since we have a coefficient of minus 1 with the y, we get a minus sign outside, right? So the next derivative is del y by del z. So del y by del z. So so y is given by f of z, right? So this is basically f dash of z, you can say. So usually we'll consider, so if you consider f as, so say f of z is equal to kz, right? So it is some sort of linear activation. Then this implies that del y by del z will be equal to k. right? And finally the last derivative is del z by del w. So del z by del w is given by, so z is equal to w1 x1 plus w2 x2 plus w3 x3 all the way up to wn xn depending on how many inputs you have. So say I calculate this for w1, so say my entire derivative thing is for w1, I'm calculating everything for w1, right? So del z by del w1 will be equal to, so what is the coefficient of w1? The coefficient of w1 over here is x1, right? So this will just be equal to x1. So finally we have we'll have del j by del w1 equal to minus of t minus y into k into x1, right? Similarly we'll have del j by del w2 equal to minus of t minus y times k times x2. So, and similarly this goes on for all the w's that we have, right? So this was what I wanted to refresh. So this is how we get the formula for perceptron, the formula for the derivative of the cost with respect to weight for any perceptron or any neuron in a neural network. And we'll use this concept in the further examples which we consider. So let's move on to some problems. The first problem that I have here is, so I have a set of inputs to a perceptron and I have the corresponding target values. I also have the activation function over here. So this is called a leaky ReLU activation function. It's called leaky ReLU. It's called leaky ReLU because you see in a normal ReLU function, the regularized linear unit function, you'll have this slope to be equal to 0, the slope when x is less than uh, 0. But in a leaky ReLU case, we take a very small slope compared to the slope when x is greater than 0. So here we have taken y equal to 0.1x when x is less than 0 and y equal to 3x when x is greater than 0. So we have here that the weights are initialized as 2, 3, 5. The bias weight is 1 and the learning rate is also 1. Right. So we'll assume the bias here, the bias I'm assuming here equal to 1 since it's not mentioned. I'm assuming it to be 1. Usually it will be mentioned in the question. So either the bias or the threshold will be mentioned in the question. So the bias weight is 1, learning rate is 1. I have my inputs here. So let's start. So the first step 1 will be, so I have my x1, my x1 vector, which I'll write as, first I'll write the bias and then the three inputs, right? So this first one is the bias, so this one is the bias, then 1, 2 and 0, right? So this is my x1. I have my w1 which is equal to, so the bias weight comes first, 1, 2, 3, 5, right? So what is my weighted input? So weighted input is equal to, so I have to multiply w1 times x1, right? So I multiply the corresponding entries, so it will be equal to 1 plus 2 plus 6 plus 0, right? So this is equal to 9. Okay. So then after calculating the weighted input, what I have to do is I have to calculate I have to calculate the activation basically. So the activation in this case is y1. I'll call it y1. So y1 is equal to 3 into 3 basically. Sorry, it's 3 into 9. So it's 3 into 9, which is equal to 27, right? So my y1 is 27. My target value here, as you can see, is for the after the first example is equal to 0. So so t1 is equal to 0. This implies that t1 minus y1 is equal to minus 27, right? So and finally I can calculate the, so in order to update the weights, I need to calculate the derivative with respect to the derivative with respect to the weights. So I have my weight here w1, right? So in the previous clip, in the previous slide, we saw that the weight is given by minus of t minus y into k into x1, right? So even in this case, I have my uh, so I have t1 minus y1 is equal to minus 27, right? So what I'll do is I'll calculate my updated, I'll calculate del j by del w1 basically. So that is equal to uh, minus of t1 minus y1 y1 times k. So k in this case is, so y is equal to 3x, so k is equal to 3 into x, right, x1, right? So this is equal to minus 27 into 3 into, so I have my x1 here, which is 1120, right? So this will give me, so this is an extremely negative number. So what this will give me is, so if I do 27 into 3, so it's 81, right? So this will give me, oh okay, by the way, this negative gets cancelled with the, so this minus sign was already there in t1 minus y1, so it gets cancelled with the negative sign in the next step. So this will be basically so this will be 81, 81, 162 and 0, right? So this is my del j del w1. And finally, if I want to update my w1, so my w1 gets updated to w2, right? So for the next step, I will use these new weights. So that gets updated to w2 is equal to the initial weight vector 1 2 3 5 minus the learning rate, which is 1, times the del j by del w1. So that is equal to 81, 81, 162 and 0, right? So this will become minus 80, minus 79, minus 159, and that will remain as 5, right? So this is w2 now. Now for step 2, I will have x2 is equal to 0, sorry, so I have to write the bias first, right? So it will be 1 0 1 minus 1, right? And my w2 is equal to minus 80, minus 79, minus 159 and 5. So weighted input again is equal, so weighted input will be this will be equal to minus 80, minus 80 plus the 79 is multiplied with 0, minus 159 minus and the 5 is multiplied with negative 1, so minus 5, right? So this is equal to minus 244, right? So when the weighted input is negative, now you see that we have to use this branch, right? We have to use this the when x is negative branch. So in this case, the derivative of y with respect to z will be equal to zero point 0.1 instead of 3, which we used in the last step, because in the last step the weighted input was positive, so we used y equal to 3x. In the second step, the weighted input is negative, so we'll use y equal to minus zero point 0.1x, right? So your y2 will be equal to minus 24.4 basically, right? And from here again, you can the target is 1, so you can calculate the difference. You can calculate del j, you can calculate this del j by del w2 again. So in place of x1, we'll put x2 here, which is 101 minus 1, and we'll continue with with this process until we reach w4 or w5 basically. The final weights after calculating them for the last example is the answer for this question, right? So it's a very long process, I'm not going to do all of it. This is how you proceed, and it's the same repetitive calculation at every step. So there's nothing much to explain there. Once you get the final weights, that is the answer, right? So the main concept here which I wanted to highlight was this concept of leaky value. In case you have your weighted inputs to be negative, you can still, instead of just replacing them with zero, you can still choose to keep them with a very low coefficient, right? So in this case I've chosen a coefficient of zero point 0.1, right? So the output from the second example, so the y from my second example will be minus 24.4. And again I have all my I have all my derivatives, and you have to be careful to change this derivative based on whether you're using the positive branch or the negative branch, right? So that is what I wanted to highlight in this question. So we'll move on to the next question, which is so we didn't use this page much. So the next question, in which I have this neural network over here, and you can see I have the target value. So I have to calculate the output y, as you can see here. So we have to calculate the output y of this neural network. I have the target value here, and we'll also calculate the we'll also do back propagation on this neural network and calculate the derivative with respect to every neuron, right? So we have also been given that it has identity function activation, so we don't need to worry about so once we get some output value for this neuron, the value is the neuron output, since the activation is equal to x. So the activation basically is y equal to x, right? So identity function, right? And my learning rate is zero point 0.8, so this will be used when I'm updating my weights, right? So first let's calculate the output y. So to get there, we have to calculate the outputs of all of these neurons, 1 2 3 4 5 6, as marked here. So I'll call the output for each of them as y1, y2, y3, y4, y5, and y6, right? So let's start. So y1 is equal to, so x1 and x2 are 1 and 2, right? So y1, the value for y1 will be this value plus this value, right? The two branches which are marking, right? So y1 is equal to zero point 0.4 into 1 plus zero point 0.1 into 2, right? So this is equal to 0.6. Similarly y2, so y2 is equal to, y2 will be equal to this branch plus this branch, right? So that is equal to zero point 0.3 into 1 plus zero point 0.3 into 2. So this 0.3 plus 0.6 is equal to 0.9, right? Oops. So y3 now, y3 is equal to, so it's equal to this branch plus this branch, right? So y3 is now zero point 0.4 times 1 plus zero point 0.6 times 2. So this will be equal to zero point 0.4 plus 1.2, which is 1.6, right? y3 is 1.6. Let's move on. So y4, now y4 is this value, this branch plus this branch plus this branch, right? So the blue and the blue are kind of overlapping, but anyway it is 0.7 times y1 times the value of y1, which is 0.6. It's zero point 0.6 plus point, so this branch over here has a weight of 0.5, so plus 0.5 times 0.9 plus zero point 0.1 times 1.6, right? So if you calculate this will come out to be, so 0.7 times 0.6 plus 0.5 times 0.9 plus 0.1 times 0.6, right? This is equal to 1.03, right? Next we have y5, which is equal to, so y5 again is equal to this branch plus this branch plus this branch, right? So that will be 0.1 times 0.6 plus 0.1 times 0.9 plus 0.4 times 1.6 is equal to 0.06 plus 0.09 plus 0.4 times 1.6, right? So this is equal to 0.79. And finally y6. So finally we have reached the end. So y6, which is equal to y, which is equal to so this is 0.1 times y4, which is 1.03 plus 0.1 times 0.79, right? So this value comes out to be this 0.182, right? So this is my value for y. My target value is given here 0.554. So we'll move to the next page. So my t is 0.554, y is equal to 0.182. So now for a neural network, we'll calculate something called the delta. So the delta is equal to basically t minus y, right? So delta is t minus y. And then for every neuron, we'll have delta 4, delta 5, delta 1, delta 2, and delta 3, right? So I'll get to how we calculate them. First, let's calculate delta. So delta is equal to just 0.554 minus 0.182, so is equal to 0.372, right? Sorry. So now delta 4 is given by this weight. So this weight W46 times delta, right? Similarly, delta 5 is given by, so I'll write it below instead of here. So let's quickly write this. So delta 5 is given by W56 times delta, right? So let us calculate both of these. So delta 4 is equal to W46 times delta, is equal to 0.1 times 0.372, is equal to 0.0372, right? Similarly, delta 5 is equal to W56 times delta, is equal to 0.1 times 0.372, which is 0.0372. Okay, now we move on to the previous layer. So delta 1 here is given by, so you see delta 1 is connected to two neurons, right? So it is connected to the neuron 4 and neuron 5 as well, right? So this will be equal to W14 times delta 4 plus W15 times delta 5, right? Similarly, for delta 2, it will be W24 times delta 4 plus W25 times delta 5. Right, so we'll calculate all of these values. So delta 1 is equal to W14 delta 4 plus W15 delta 5. So you can see delta 4 and delta 5 are the same. So I'll just add the weights and multiply it with the delta 4 delta 5. So the weights here are 0.7 and 0.1. Right, so we'll have 0.8 times 0.0372, which is equal to, is equal to 0.02976, right? Similarly, delta 2 is equal to W24 delta 4 plus W25 delta 5, right? So this is equal to, again I'll just add the weights. So the weights here are 0.5 and 0.1, right? So it is 0.6 times 0.0372, right? So this is equal to 0.6 times 72, 0.02232, and delta 3 is equal to W34 delta 4 plus W35 delta 5. So this is equal to, so the two weights in this case are 0.1 and 0.4, right? So it is 0.2, 0.1 plus 0.4 is 0.5. So 0.5 times 0.0372 So that is 0.0186. Right. So we have all the deltas. So we have delta 1, delta 2, delta 3, delta 4, delta 5. Right. So and we have the final delta, which is delta 6, if you want to consider that. So now we can update the weights as, so this weight over here, so this weight, I'll mark it in red again. So this weight over here is wx1 time 1, right? So it connects the input x1 to the first neuron, right? This is wx1 2, this one. So I'll use the same color code which I was using before. So again, this weight is wx1 x1 1. This other red weight is wx2 1, right? So let's calculate these two first. So wx1 1, so this is given by the previous wx1 1 minus alpha times delta 1, alpha times delta 1 times x1, right? So this is the formula, and by replacing all the values, so wx11 was zero point 0.4, so zero point 0.4 minus 0.8 times delta 1 came out to be 0.2976 times x1 is equal to 1, right? So you can calculate this value. Similarly, wx2 1 is equal to the previous one minus alpha times delta 1 times x2, right? So since it's connected to neuron 1, so since x2 is the input connected to neuron 1, we use delta 1 and multiply it with x2, right? So this will be equal to, so the weight here was zero point 0.1, right? So the weight here was, yeah, it is zero point 0.1. So zero point 0.1 minus 0.8 times second delta 1 is 0.02976, but x2 is equal to 2, right? So you can calculate this as well. Similarly, once we, so again we'll have, the next two weights are wx2, wx1 2 and wx2 2, right? So these are given by very similar formulas. So wx1 2 is w, the previous one, minus alpha times delta 2, since it's connected to neuron 2 is delta 2 x1, right? We'll get some value over here. wx2 2 is given by wx2 2 minus alpha times delta 2 times x2, so we'll get that. Similarly for the this third a neuron as well, we'll get, so this is wx1 3 and wx2 3, right? So we'll have, so wx13 is given by wx13 minus alpha times delta 3 times x1, and this is the same, wx23 minus alpha times delta 3 times x2, right? So now we move to the next layer. So if you want to calculate this weight, so I'll mark it in blue again. So this weight over here, so this is w14, right? So w14, the updated value is given by the previous value minus alpha times delta 4 now into y1, right? So we'll use the activation, right? So we'll use the previous activation for to calculate this as y1. So we'll get some value over here. We had already calculated y1 to be equal to 0.6, right? So we'll put that value 0.6 over here. We have delta 4, we have all the other values. Similarly, w15 is equal to w15 minus alpha times delta 5 times y1, right? And similarly for w24, w25, w34 and w35, right? So we can calculate all of these values. And finally, if you want to calculate w46 and w56, then those are given by w46 minus alpha, alpha times delta times y4, and this is given by w56 minus alpha times delta times y5. So delta is equal to this value over here. So delta is 0.372 then. Okay, so this is how you calculate all the weights, all the updated weights. And after calculating all the updated weights, then we move on to the next iteration of the neural network. So if you have some more so if you have some new x1 x2, we'll use the new weights and the new x1 x2 to calculate another y, over here. And then we'll have some new target value also, hopefully. And then we can calculate the new delta and the new delta 4 5 delta 1 2 3, and we'll again update the weights. So this is how the network continuously updates its weights to match the training examples which is given. So all of this sounds really complex on paper, and it is really complex to do on paper, as you can see here. But in a computer, all of these calculations can be done using some simple matrix multiplications, which make our life much easier. So a computer is able to do all of these calculations really fast, and we can easily get a trained neural network which is trained on our a specific training set, right? So this is all the problems that I wanted to discuss for this week. I hope you understood all of them, and yeah, see you again next week. Thank you.